Hello students, welcome to the fourth part of noise analysis video series. In this part, we'll discuss about different types of noise sources that exist in CMOS circuits. But before that, we'll just revise ourselves the terminologies with respect to frequency domain and time domain of noise sources. As we know, if the random process is a voltage source, then its power spectral density is denoted by S sub V of F, and its unit is generally given as volt square per hertz. On the other hand, if the noise source is a current source, then its power spectral density is given with this term, which is S sub I of F, and its unit is going to be ampere square per hertz. Now, both these quantities are specific to frequency domain. And later we started using the Wiener-Kitchen relation to convert this power spectral density into an autocorrelation function. Now, because the random process is so random that the autocorrelation function will have a non-zero value only when tau, that is equal to 0. So under such condition, one could convert the power spectral density by making an integral from minus infinity to plus infinity across the power spectral density of a random variable x in the frequency domain, and this result in turn gives us what is known as the total average power in the time domain. Now, in case if this power spectral density is being evaluated only with a specific zone of frequencies or specific band of frequencies, say for example, it is being evaluated between the frequency f1 to f2, then the result of this integration will then give us what is known as the variance or the mean square value. Or it can also be called as average power. But we'll not use this term average power for the variance, but rather we'll use it for the total power computation. Later, we looked at three important properties of power spectral density and variance. So among the three, the first two are the properties that are specific to the power spectral densities. So let us look at each of them and make a quick review about them. So the first property is nothing but the spectrum shaping property. Now, this is something where when you consider a system which is an LTI system having a transfer function h of f, then if the input to this system is denoted by x and the output of the system is denoted by the signal y, then one could evaluate the output power spectral density of this transfer function h of f by writing down this output power spectral density as S sub y of f is equal to the modulo of this transfer function square times that of the input power spectral density of the signal x. And this is one of the major important property that we'll be using throughout this coming videos. The next property that we looked, the conversion of a two-sided power spectral density into a single-sided power spectral density. So which means that a two-sided power spectral density could be written as just a product of one-sided power spectral density, provided this two-sided power spectral density is symmetric about the frequency 0. So only then we can use this. So we'll not use much of this property in the coming videos, but still it is worthwhile to recollect what we have discussed. And the third important property is a property that belongs to a time domain. Consider that there exists some set of noise sources inside the circuit. Now one could write the total power contributed by each of these noise sources as the summation of each individual noise sources that exist inside the circuit in terms of powers. So note that in order to calculate the total output power, we are calculating the noise contributed by each individual source power terms. It is not the addition of the sources and then taking the whole square of it. Hope that you're clear, and this becomes much more clear when we do some set of problems. So now let us come back to our discussion about different types of noises in the CMOS circuits. One could broadly classify the type of noise that exists in the MOS transistor circuits as two categories. One we call it as a thermal noise, the other one is the flicker noise. So in this video, first we'll discuss about the thermal noise, and in the next video we'll discuss about this flicker noise. Now let us try to understand what is this thermal noise. A thermal noise is a noise that happens due to the random motion of electrons inside the conductor. And this random behavior of the electrons or the charges is basically a function of time. And this thermal noise exists both in the resistor and the MOS circuits. So since they exist in both these circuit elements, we'll first address the thermal noise that exists inside this resistor. Followed by this, we'll try to discuss about the thermal noise inside the MOS transistor. So consider a very simple circuit setup where a potential DC voltage is being applied across a resistor which is noisy. So one could write the instantaneous current flow through this resistor as just V by R, and this is a quantity that one would end up having when we have some sort of forced signal onto this resistor. So I would call this particular term as forced response. But as we discussed in the earlier video, we know that even in the absence of this voltage source, there exists some sort of noise component through this resistor, such that the instantaneous current not only contains this forced response, but also it will have the noisy component superimposed on this forced response term. So the term which is denoted as I sub n of t with a bar at the top denotes the RMS value of our noise current. So this one is again, it's the instantaneous current component, and the first term represents the forced response of the system, and the second term represents the RMS value of the noise current source. Now clearly one could represent this noisy resistor in terms of a noiseless resistor plus some sort of noisy component associated with it. So what I really mean here is that one could represent this noisy resistor with a circuit element where we have an R which is completely noiseless, and along with this one could add a voltage noise term or the root mean square value of the noise source in series with it, or one can also have one more circuit representation for this noisy resistor as a noiseless resistor in parallel with a noisy current source. So again, what we are representing here is an RMS value of the noise current component. So there are two equivalent representation for this noisy resistor. So now let us try to see what is the power spectral density of this noisy voltage term, and then later we'll also try to discuss about the power spectral density of this noisy current term. So we have used one of the representation over here where the noisy resistor is being represented as a noiseless resistor in series with a noisy voltage term here. Now in your textbook, rather than representing this voltage noise as an RMS value, they have used the mean square value or the variance term over here. So one should not get confused with the mixed usage of either a mean square value like this or the RMS value like this. And the reason why we represent the voltage noise source as a mean square value or the variance would become obvious when we discuss about certain problems in the coming slides. So till then, one would represent a noisy resistor as a kind of circuit which is decomposed into a noiseless resistor in series with the mean square value or the variance of the noise voltage. Now this variance term will have a corresponding power spectral density, and one would write the power spectral density as S sub V of F to be equal to 4 kB T times that of R. Now in this, the term kB denotes the Boltzmann constant, which is equal to 1.38 into 10 to the power minus 23 joules per Kelvin. And the T term represents the temperature term in terms of Kelvin, and R is nothing but the value of the resistor. Now clearly, as you could be able to see, that the power spectral density term doesn't have any frequency associated with it, which means that the power spectral density is constant throughout this frequency range. And we look carefully that the power spectral density of this term is represented for a frequency from a value of 0 to all the way to infinity. But in reality, the power spectral density of a thermal noise never reaches a frequency which is equal to infinity. But in the circuits that we deal, goes all the way to somewhere around gigahertz. When we look at the power spectral density of a voltage thermal noise, the spectrum of that power spectral density is constant till a terahertz range. So due to which one can assume that this power spectral density is constant right from frequency that is equal to 0 all the way to infinity. So now that we have discussed about the power spectral density of a voltage thermal noise, but what about the power spectral density of a thermal current noise? So in order to compute this power spectral density of a current noise through the resistor, we'll be making use of the spectrum shaping property that we had discussed as the first property. Now the only thing that we are being asked to compute is the power spectral density of this noise current source. Now in order to compute this, what we wanted is, we have a system and we need to compute the transfer function of this particular system, right? So at the input, we know the power spectral density of a voltage noise, so which means that I know what is SV of F, and what we wanted to know is the power spectral density of the current noise. Now in general, the transfer function H of S is defined as output term divided by an input term. So at the output we are expecting a current, whereas at the input we are feeding a voltage. And from the simple Ohm's law relation, one could write this I by V as nothing but 1 by R. Now that is the transfer function, bringing the input, that is voltage, and to the output, that is current. Having got this transfer function, now let us try to evaluate the power spectral density of the noise current. One could make use of this first property, which is nothing but, it's a product of modulo of the transfer function times that of the input power spectral density, which is in terms of voltage. And the value of this transfer function, when we put under modulus and then square it, we would end up having 1 by R square, and that is being multiplied with the power spectral density of this voltage noise source, which is nothing but 4 kB T times that of R. So clearly there are some common terms that we have here. So once we cancel out those common terms, we would end up having something like 4 kB T divided by R, and that is the power spectral density of a noise current component. So now let us look at the power spectral density graph of it. Now again, one could see that this power spectral density term is not a function of any frequency term, and because of which the power spectral density of this noise current source runs from 0 to all the way to a frequency which is infinity here, and throughout this entire zone it is assumed to be a constant value. Now let us quickly do a small exercise problem. Let us consider a resistor whose value is 50 ohm and it is held at a temperature of 300 degree Kelvin. And now what is the thermal noise voltage that is exhibited by this resistor? Now in order to compute this, first we need to calculate the power spectral density of the voltage noise source, which is S sub V of F, and we know that the expression for this is given by 4 kB T times that of R, and the only thing that we need to compute is to plug in all these quantities from the given value set. So again, one has to remember the value of this kB in case if it is not given in your problem set, which is nothing but 1.38 into 10 to the power minus 23, and the value of T is given here as 300 Kelvin. So ensure that it is given in terms of Kelvin, just because the Boltzmann constant is specified as joules per Kelvin. So due to which we have to have a Kelvin term here, and in case the temperature T is given in terms of Celsius, one has to convert in terms of Kelvin and then plug in here. So this has to be multiplied by the value of the resistor, which is 50 ohm. Now once we multiply all these terms, one would end up having a value which is equal to 8.28 into 10 to the power minus 19, and the unit of this power spectral density is given as volt square per hertz. But what was asked in the question is not the power spectral density, but rather the thermal noise voltage, which means that we are looking for RMS value of a voltage noise. Now in order to evaluate this RMS value, first we need to translate this quantity, that is the power spectral density, into a variance, for which one could use the Wiener-Kirchhoff relation, where the frequency has to be either run from minus infinity to plus infinity or between the set of frequency of F1 to F2. So now in either cases there is no frequency term that is given in this particular problem set. So now what we do is that let us assume that we'll use the variance computation of this autocorrelation function, which is nothing but it's an integral that runs between a frequency F1 to F2, integrating over the power spectral density with respect to frequency. Now since because the power spectral density is independent of any frequency term, one could pull out this power spectral density out of this equation, and when we perform an integral between F1 to F2 with respect to the derivative of frequency, one would end up having a value which is SV of F into delta F, where delta F is nothing but F2 minus F1. One could use that the value of delta F to be equal to 1 Hertz. Now whenever we are being asked for thermal noise voltage, and if there is no specific set of frequency band that is being specified, then one has to compute the variance where the frequency band delta F is always considered as 1 Hertz. And the value that we would get out of this expression is nothing but the mean square value. Okay, yeah. So one thing that one could observe here is that the variance is exactly equal to the power spectral density. So this happens whenever the power spectral density is constant, that is, it is not a function of any frequency term, and if the frequency band is not specified, then the value of delta F is considered to be 1 Hertz. So under these two conditions, one could write that the mean square value is exactly equal to our power spectral density quantity. The mean square value will have a unit of volt square, whereas the power spectral density will have a unit of volt square per hertz. So now that we have got the mean square value, but what we wanted is a RMS value. Now in order to compute the RMS value, one could make a square root of this mean square value. So taking a square root on this particular value will then return us a quantity which is equal to 9.1 into 10 to the power minus 10 volt, and that is the thermal noise voltage in the circuit. Now let us make a quick comment about the noise that comes out of any given circuit element. Now let us consider a circuit that has a resistor and a capacitor, now among which the noise in general is contributed only from a dissipative element. So which means that a resistor, as we know, is a dissipative element, and whereas a capacitor ideally is a storage element. So among these two elements, it's only the resistor that contributes to the thermal noise. It's not the capacitor. So this is an important note that has to be remembered when we try to analyze any noise analysis for the given circuit. Now what we do is that let us quickly apply this concept onto our next problem set. But before that, let me summarize some of the procedure set that we need to follow when we perform a noise analysis. The first step is that for a given circuit, kill any input signal sources of the network. So here one has to clearly ensure that we are not killing the noise sources, but what we are killing is the input signal source. Okay, so this is an important term that has to be considered. And the second step is to identify various sources of noise that exist inside the circuit. The third step is to calculate the individual noise contributed to the output of the network. And the final step is to sum all these noise contributions, and if required, one has to compute the total noise power at the output port. So these are the four set of procedure that one has to follow when we perform a noise analysis. So now let us move on to our problem set. So here is a case where we need to consider an RC network, and we are being asked to compute two quantities here. One is the noise spectrum at the Vout port. So noise spectrum is nothing but we have been asked to compute the SV of F term, and we are also being asked to compute the total noise power. So in this case, one has to compute the autocorrelation function based on the value that we computed from the power spectral quantity. Because we are being asked to compute the total noise power, the integral has to run from minus infinity to plus infinity. Okay, yeah, so hope that you are clear with these terms before we actually begin solving this particular problem. Now we have two components, a resistor and a capacitor, but among these two components, if at all, if we assume that the capacitor is an ideal storage element, then the noise will only contributed from the resistive network. So now let us try to evaluate the noise contributed by this network. So let us try to follow the set of procedures that I have listed before. The step number one is to kill input sources, which is basically an input signal source to the network. So in this case, one could able to see that there is no voltage term or the current term that is fed as an input to this particular network. So this step is not required in this particular circuit. So let us move on to the second step, where one has to identify the different sources of noise that exist inside this particular circuit. Now we have two components here, among which the capacitive component will not contribute to any type of noise, and it is only the resistor that contributes to the noise. Now as we know that this noisy resistor can be redrawn into a resistor which is noiseless in series with a voltage noise source, or a noiseless resistor in parallel with a current source noise. So one has to think like which among these two representation can be used such that it gives us an easier way to compute the transfer function. Now I would prefer to go for the series connection, and that would end up having something like this. Okay, yeah. So now clearly one could see that the noisy resistor is being replaced with a noiseless resistor R, and along with a capacitor C here. Now one has to evaluate the transfer function of this noiseless component. Now again, we have a system or a network where the input is a voltage term, which is V, and the output is also expected to be a voltage. So the transfer function H of S would then be returned as output component divided by the input component, and in our case it is V out by V in term. Now we know this V out by V in term is a simple RC network, and one could write the V out as 1 by j omega C for the capacitive element times that of the current into the current flow through this resistor in series with the capacitor term multiplied by the current, so that the currents can be cancelled out here. So in general, the transfer function will then be returned as something like 1 plus j omega RC. So having got this, let us try to evaluate the output power spectral density in terms of voltage. So since we have both input and output in terms of voltage noise sources, rather than writing the output noise source as S sub V, I will use it as S sub out of F, and the input power spectral density as S sub in of F. So one could make use of this spectrum shaping property, which is defined as the modulo of the transfer function square times that of the input power spectral density S sub in of F. Now we know that this noise component, which is a voltage component, will have a power spectral density which is given by 4 kb T times that of R, and this is the spectrum of S sub in of F, so that we can just plug in here as 4 kb T times that of R, and we also know that this quantity is taken under the modulus and then squared, and because of that one could write as something like omega square RC square. Okay. Now when we look carefully, that the output power spectral density of this network has some sort of pole term, and the pole in short exists at a particular frequency which is defined as 1 by RC. Okay, so we have a single pole system, and that pole exists in this particular frequency, and because of which a resistive power spectral density, which has a constant power spectral density, when it is being passed through this RC network, it gets shaped into a low pass filter characteristics. And now that we have computed the first term, that is the noise spectrum at the output, which is given by this term. Now one has to evaluate the total average power at the output node. So in order to calculate that, one has to use the Wiener-Kitchen relation, which is nothing but taking an integral from minus infinity to plus infinity over this power spectral density, which is specified as S sub out of F into dF. Now clearly one could see that the power spectral density of the resistor or the power spectral density at the output of this RC network starts from a frequency which starts from 0. So because of this, one has to rewrite this entire expression from 0 to infinity, and this will return us the total noise power at the output. Now let us try to bring our expression onto this integral. So clearly from the calculus we know that whenever we have an integral of this particular form, which is given by dx by 1 plus x square, then the integral of this particular quantity will return us a tan inverse of x term. So we'll be making use of this particular property over here. But before we do that, let us try to map the term x with respect to the expression that we have. So one could write, just by making a comparison, that the term x is given by this quantity, which is omega times that of RC, and in the place of dx we have to have a differentiation of this particular quantity. So I'll just expand this omega as 2 pi f times that of RC. Now when we try to differentiate with respect to the frequency, then we would end up having something like 2 pi RC into df. So because of this dx quantity, one could multiply this term as 2 pi RC divided by 2 pi RC term. So now we have a situation where the set of quantities maps onto this particular expression, and again one could cancel out some of the common terms that exist out of this particular boundary. So we have an R term which could be cancelled out from both these expressions, and we also have this 2 being cancelled from the 4, and yeah, so again this 2 kb t divided by pi c is completely a quantity which is constant, so one could bring out of the integral as okay. Yeah, so now that we have brought this, and the integral is exactly in the form that we wanted, which runs from 0 to infinity, and then we have 2 pi RC times that of df, which is reflecting the quantity of dx term, and at the bottom we have 1 plus omega RC the whole square, which is reflecting the term of x here. Now clearly one could rewrite this integral as 2 kb t divided by pi c into tan inverse of this entire term of x, and runs at the limit of 0 to infinity. And we know that a tan inverse of infinity is nothing but pi by 2, but a tan inverse of this limit of 0 is actually equal to 0. So out of this tan inverse term, we would end up having a value which is equal to pi by 2, and outside this integral we have this constant term, and again one could cancel out some of the common terms out of these expressions like pi and the value of 2. So the total power of this network is nothing but kb times that of c divided by c, the capacitive component c. There are few observations that one could make out of this expression of P total. Note that the total noise power is completely independent of the resistor value that we have used here. This means that the area under this output power spectral density for any value of R would then remain same. That is, let us consider two resistors R1 and R2 such that the value of this R1 is larger than the value of R2, and the corresponding power spectral density of each of these resistors is being shown here. Since because the value of this R1 is high, its power spectral density magnitude will be higher than compared to the power spectral density of this resistor R2. When these resistors are being combined with the capacitor, we know that the RC network will then create a low pass filter configuration. Now, in the case of a resistor of R1, the combination of R1 with capacitor results in a smaller bandwidth, which is defined as omega minus 3 dB is given as 1 by R1 times that of C, and since the value of this R1 is high, the bandwidth would be smaller here. Whereas in the case of a network where we have a resistor R2, then this will have a bandwidth which is quite larger than compared to the bandwidth of the R1 combination. Now, because of these differences in the bandwidth, the output power spectral density of this RC network will then be having a different type of shapes. So as I said before, since the bandwidth of R1 is small, you could able to see that the width of this frequency component of the output power spectral density is generally small, whereas the width of the power spectral density in the case of an R2 is quite wider. But what about the heights here? As you could able to see that the height of this power spectral density is higher than the value of R2, and clearly one could see that when we perform an integral over this power spectral density at the output of the RC network, which is nothing but the computation of area under these graphs, the area would then remain the same, and that area value is given by this Boltzmann constant times that of the temperature divided by the capacitive element. Now, in case if one wants to reduce the noise contributed by the resistive component, it is not the R that we need to change, but rather it is the capacitive load that one has to increase in order to reduce the noise contributed by the resistor, which is thermal noise. Now, let's do a third example, which is to compute the equivalent noise voltage of a two parallel resistor R1 and R2. Let's again try to understand the question first. The question asks us to compute the noise voltage, which means we are being asked to compute the RMS value of the noise sources, and that noise source element supposed to be in terms of voltage. So as a first step, we have to kill an input signal source here. Now, as the given circuit doesn't have any input source, we can skip the step number 1. So the next step is to identify the noisy element out of the circuit. So in this case, it is the resistor R1 and the resistor R2 both contributes to the noise in the given circuit. So one could redraw these elements which are noisy in terms of noiseless element in combination with the noisy element. Now, as we did in the exercise number 1, one could redraw this noisy resistor either as a noiseless resistor in combination with a voltage noise source, or a noiseless resistor in parallel with a noisy current. Now, which among these two configurations would better suit this particular circuit analysis? As we know, since the resistor R1 and R2 appear in parallel, it is better to go with this combination where you can replace the noisy resistor as a circuit with a noiseless resistor in parallel with a noisy current component. Now let us do the same. When we do this, one would end up having a structure which would look something like this. Now again, from the property number 3, we know that one could combine average power of each individual noisy elements, right? So what I'm going to do is that I'm just going to combine these two noise components, and since they are appearing in parallel, one could redraw this structure as a network where we have a noiseless component inside this network, and the input to this network has a noisy resistor, which is nothing but the summation of these two average noise powers. So now the combination of this input noise current sources is nothing but written as 4 kBt times that of R1 plus 4 kBt times that of R2. So clearly we have a numerator term which is common to both, so I would pull out these common terms out of this expression so that I have a neater expression, something like this. Now again, the combination of this is nothing but it is written as R1 in parallel with R2, and that is the total effective power spectral density at the input noise current source. Now that we are being asked to compute what is known as the output power spectral density in terms of voltage. Now again, one could make use of this spectrum shaping property, which says that in order to compute the power spectral density in terms of voltage, one has to know what is the transfer function of this noiseless component. And again, one could think that h of f is defined as output component divided by the input component, and in this case the output component we are looking for is a voltage divided by the input component that we are feeding here is a current. So we know from the Ohm's law that the value of this V by I returns us a resistive element. Now this resistive element is nothing but the combination of R1 in parallel with R2. So now that we got the transfer function of it, let us try to plug in into our expression, and it is R1 in parallel with R2 the whole square into this input noise current source power spectral density, which is 4 kBt divided by R1 in parallel with R2. So effectively we can cancel out some of the terms here, and one would finally end up having the power spectral density at the output as something like so again, one could see that what we have got right now is nothing but the power spectral density, but what was being asked over here is the RMS value of the noise voltage source. So clearly one has to use the Wiener-Kirchhoff relation in order to convert this power spectral density into the mean square value or the variance. So let me write that as Vn out square, which is evaluated from this power spectral density SV of f into df. But right now we know that we are not being asked for the total power, so the integral cannot run between minus infinity to plus infinity, nor we are being given a specific set of band to be computed, and due to which the band difference between this frequency f2 to f1 could be considered as 1 Hertz. So again, when we look carefully, the power spectral density doesn't have any frequency term inside this, which is completely a constant, due to which one could take out this power spectral density term out of this integral, and when we perform the integral with respect to the derivative of f, we would end up having a delta f, and since the frequency band is not given, one can consider that the band is to be equal to 1 Hertz, and due to which the expression of this power spectral density in short gives us the variance of this particular network. So now that we got the variance value, the RMS value is just taking a square root on this. That's it. So now let me give some sort of assignment. I want you people to calculate the equivalent noise current. Okay, so what we are looking is a noise current for a network that is composed of two resistors which are in series. And with this, let me stop the discussion about the thermal noise from a resistor. In the next video, we'll begin with the discussion of thermal noise from the MOSFET. Thank you.